I'm really honored and really grateful to the organization that I get the opportunity to open this conference. I'm already really impressed. It seems they run a very tight ship. The title that you have on your booklet is unfortunately not the right one. I'm filling in a little bit last minute for another speaker, so I will not be telling you how to improve your craft through communication, but I will go straight into a more technical topic, namely about clojure.spec. Real quick, who am I? So my name is Arne Brasseur. I'm Plexus on Twitter. And what I do is create screencasts about Clojure. So I only launched this a couple months ago. I'm trying to turn this into a sustainable business. So if that kind of stuff interests you, do check it out, lambdaisland.com. That's all I'm going to say about that. Today we're talking about clojure.spec. So I know not everybody here does Clojure, but I still think there's interesting stuff to take home from that, and so I'll try to make it self-contained and give you everything you need to know. So in the upcoming version of Clojure is currently still 1.8, but the 1.9 version is in alpha. There's going to be a new library that ships built in with Clojure called clojure.spec. And what it basically does is give you a syntax for describing your data, describing the shape of your data, describing what valid values are. It's kind of like a schema language. And so it lets you validate data. That's kind of the obvious thing. But there's also other things you can do with that. And I'll talk much more about that in this talk. Now, before I really dive into it, I quickly want to say something. So I know that some of you in the audience will be thinking, my type system can do that. And that's great. But if that's going to be your first question after the talk, then please just let somebody else ask a question. So Clojure is a dynamic language that ship has sailed for better or for worse, but you know it has pros and cons, and that's just how it is. But still, it's interesting to look how then a dynamic language deals with some of these same concerns that maybe in your statically typed language you would deal with using a type system. Now, one thing that maybe is interesting to point out is that in a statically typed language, you get a lot of this stuff at compile time, which is really nice and which we can't really do. You get most of this stuff at runtime. But you also get a little bit of interesting things at compile time, and I'll talk about that later towards the end. So this is more or less what we have on the agenda. So I'm first going to say a few words just about Clojure data, what Clojure data looks like, because you know it's kind of important to really understand the design decisions and how this whole thing works together. And then there are two sort of perpendicular topics to explore. One is, okay, how do I create these specs, these schemas? And the other is, what can I do with them? How do I use them? So I'm first going to give you an example, sort of high level as an introduction, not go too deep into it, show you how to make some specs, how to use them, and then I'll cycle around, take it back from the top, but dive a little bit deeper into some of those aspects. In particular, I think there are some really powerful ways how to deal with and how to write specs for maps. That's one thing, and for sequences. So I'm gonna dive into those a bit more, and then I think there are two sort of more advanced, more interesting features that you can use these specs for, which is instrumenting functions and macros, and use them to drive generative testing. So we'll get to that towards the end. So data in Clojure. Clojure ships with a handful of built-in data types, but the most obvious ones, the ones that are used all over, are vectors and maps. So these are typical immutable, functional, persistent data structures. And Clojure people really like these. So you can use things like classes and types and records, so kind of like structs. But unless you really need to, for instance, for Java interop or stuff like that, people don't usually do that. So a lot of it is really just that. 90% of the data flowing through your programs are just vectors and maps. And so the result is that these maps are everywhere. And what is typically used as the keys in these maps, well, those are keywords. So keywords, some of you might know Ruby, but not Clojure, so they're very similar to Ruby symbols. They're basically lightweight, immutable strings. So they're very easy to use to do key lookup in these data structures. They're also used anywhere where you would use an enum in a language that has enums. So there are some examples at the bottom here, like, so you write them with the colon first and then followed by your keyword. Now Clojure does have an interesting spin on this. Yeah, I couldn't resist because of the title of the next slide. It's the last meme, I promise. So keywords everywhere, which means that you have a chance of collision. So if you're dealing with different libraries and you're maybe dealing with maps that have data coming from different sources, how do you know that you're not going to get the same key that's actually representing two different things? And so Clojure's answer to that is to namespace these keywords. So you see that slash in there. It's kind of saying, okay, well, you have an encoding, but in the context of my audio library, encoding can mean one thing, and in the context of another library, encoding can mean something else. And because they're namespaced, they don't clash. We get a shorthand syntax for this. So if you're in a specific namespace, I'm in the my audio lib namespace here. I'm also including the transfer namespace and alias to T. So then with colon with two colons, and then the name of a keyword, it kind of expands into the thing on the right. So this is a shorthand for writing these namespace keywords. Does that make sense? And Clojure 1.9 is going to ship with some other ways. For instance, if you have a map and every single key in that map is a namespace keyword with the same namespace, you'll get a shorthand for writing that as well. So it seems there's a general push towards encouraging people to use these namespaces so that keys don't clash. Okay, so that's the prelude. Let's talk about Clojure.spec. So here's an example of a bit of Clojure data. I have an ingredient, I have a recipe. And so my recipe consists of ingredients, which is just a flat vector and then a number of steps. Here I have a recipe for tomato sauce. And the system that we're going to build is a robo-chef. So this is a machine that stands in your kitchen and it gets recipes from the cloud and it prepares your dinner, right? Obvious, IoT and everything. So okay, let's get started. I'm in my RoboChef namespace. I want to write some specs because we want to make sure that these recipes, as they flow through the system, as they're manipulated through various functions, that they're always valid, that they always conform to a certain specification. So I've included Clojure.spec here and aliased it to S. So now I can say s/def, so it means I'm going to register a spec. I'm going to register the recipe spec. And here I'm saying that, well, a recipe, it's a map with certain keys. It needs to have an ingredients key, and it optionally also has a steps key. Like I said, this is just a first example to sort of warm up. I'm going to go into much more detail later on, so just try to get the big picture now. And then I have a separate spec to say what ingredients look like. So ingredients are a number, a keyword, a string, over and over and over. And then same for steps. Don't have that specification here. And so this adds these to a global registry. There's a global registry of specs that take namespace keywords and register a specific spec against it. So now I have a recipe spec, I have an ingredient spec, I have a step spec. What can I do with these? Well, the obvious one would be I can validate some data. So now I can say, okay, 5 grams of tea, is that a valid list of ingredients? Well, yes, it is a valid list of ingredients. Now, one other interesting thing beyond merely saying, is it valid, is that you can conform data, which basically means that it runs that data through your spec, yes, and gives you a more structured version of the same data. So you're still looking at the same data, but now instead of just that flat vector that we need to pull apart and it's less obvious what's exactly in there, we get this map representation with the keywords that we used in our spec, say that, yes, we have an amount of 5, the unit is grams, and the name of this ingredient is tea. So that's, these are some of the basic things you can do with these specs. Now, what are more interesting things you can do with spec? Well, say that I have a spec that's actually violated. So here I have a list of ingredients, but it's not a valid list of ingredients. So the first item in the list should be a number saying the quantity of ingredients. But it's not, it's a string. And so when I say, okay, is it valid? Spec tells me, no, it's not valid. So, well, okay, that's not terribly helpful. What's the problem? So Spec has a couple of functions that can tell you what exactly the problem is. So here it says that in position 0, in the first position, this value string 10 fails because the amount needs to satisfy the predicate that it's a number. So it takes a little bit of getting used to reading these error messages, but at least it tells us exactly, you know, this is where it went wrong. This is what you're doing wrong. And then, again, to give sort of finish this high-level overview, specs can also be used to generate data. And this is where it gets really interesting. So here I'm basically saying, generate for me 2 potential valid ingredient lists. And so one is the empty list, and one is a list with, you know, a quantity of 0 and a keyword and a string. Now you see that I get vectors back here, each with 2 items. So the first is the generated data, and the second is the generated data as you would get it back when you're using this conform function. So it's this sort of molded value. So when you see here amount 0, unit high, name 0, it's the exact same data as the thing before it, but because it's been run through the spec, we get it back in a more structured format. Okay, so to be a bit more systematic about our build-up, what exactly is a spec? So it starts really simple. It starts very small with predicates. So you have a whole bunch of built-in predicates, and actually also Clojure 1.9 is going to ship with a whole lot more built-in predicates in the core namespace. So that's really your starting point. Things like, is this a number? Is this a string? Is this a positive number? Stuff like that. And then you use those predicates, and you can write your own predicates to compose and combine to build bigger specs. So here we're saying, well, something can be either a number or a string. So we have the or function in the spec namespace that returns a spec object that checks that. Is it either a number or a string? Or we can say we're looking for a collection of numbers, and specifically this collection needs to be vectors. So that's what this call off function does, just to give you an example. And so any function that deals with specs can take predicates, can take some of these spec objects, or you can give it the name of a registered spec. So we saw before with this as def that we can register specs. So anywhere where you would use a literal spec object, you can also use the name of a spec. Now, there are 2 functions, 2 ways of creating these spec objects that are quite powerful and that really sort of show the underlying philosophy of Clojure spec. So I want to drill into 2 of these. One is the keys function that we also already saw at a glance at the first example. And the second one is basically a built-in regular expression engine that ships with this Clojure spec, not for strings, but for any sequence of values. So I'll explain more what that means exactly. So say you have maps. Like I said, maps with keywords, they're everywhere in Clojure. It can be something coming out of your database or something coming off the wire, or anything that's being passed around. It's 9 out of 10 times it's being passed around as a map with keywords as keys. So this is where this keys function comes in, and it tells you, okay, these are the keys that I expect. Now, the underlying idea is that the same key in a different context should always have a similar value corresponding with it. So if I have the apples key, then no matter where in the system that I have the apples key, it should have apples as values and not pairs. Now, the way it does that is by decoupling the specification of which keys it's expecting and the values that correspond with it. So you see here that I'm specifying this in 2 steps. I'm saying a recipe contains ingredients, but I'm not saying there in that first line what those ingredients are. Instead, I have a second definition of ingredients. Now, if I start to validate the recipe, spec is going to look at all the keys in that map and say, okay, do I have a register spec for this key? Then I look it up in the registry and validate the value accordingly. So what Regexp says about this is that most systems for specifying structures conflate the specification of the key set with the specification of the values designated by those keys. And this is a major source of rigidity and redundancy. So let's take our recipes. It doesn't matter if that recipe is, part of our global, like our local state of our robo chef who's doing stuff, or it's being processed by some other part and maybe it's something that's going over the wire, or it doesn't matter where in the program you have the key recipe, whatever corresponds with its value should be a valid recipe. And so S-keys will look at every key in a map, try to find a spec with that name, and then use that spec to validate the corresponding value. So what that means is that you can actually use the keys spec type without any specification of keys. So here, I'm showing that I had my original spec, which was going to check for ingredients and steps, but now we loaded an extension to our RoboChef, which says that, oh, actually now the RoboChef also needs to know how long it takes to prepare something, because your dinner needs to be ready in time. So we're adding a new key to our recipes, which is cooking time, which we didn't know anything about earlier. And in first instance, our recipe is still a valid recipe because spec doesn't know anything about cooking time, and so it just ignores it. But once we register a spec for cooking time and say that cooking time needs to be a number, then S-keys, when validated, will also find that cooking time key, find the corresponding spec, and say that, oh, actually, a cooking time always needs to be a number. Okay, the second part of Clojure spec that I think is particularly interesting and powerful is the whole system for dealing with sequences. So I already pointed out Clojure has vectors, but any collection type that you can process in a sequential manner implements an underlying abstraction which Clojure calls a seq, or a sequence. And to handle all of these in the same way, Clojure gives you a regular expression engine. Now this can be a bit of a mind twist in first instance, because regular expressions are so tied in our minds to strings. But what's a string? A string is a string of characters. And so a regular expression basically turns into a state machine that takes one character at a time, looks at the next character, and then goes along in the state machine in the regular expression. So here we have the exact same thing, but we're not dealing with characters, we're dealing with any value that you can put in a sequence. And so this whole part is based on a paper called Parsing with Derivatives. And even though it's called regular expressions and it uses a lot of logic and nomenclature of regular expressions, it's actually powerful enough to parse flat structures into nested structures. So you can do balancing of parentheses and stuff like that. It's actually powerful enough to do context-free grammars. So how does that look? So there are 5 regular expression operators that you can combine. And they should look more or less familiar. So we have 3 quantifiers, the star, the plus, and the question mark, which are exactly the same as they are in string regular expressions. So a star means 0 or 1, 0 or more of a thing. So when we have an empty vector or a vector with 1 keyword or with 2 keywords, that's all fine. But when we say plus, it means at least one of a thing. So the empty vector now is no longer valid, and we get back a special value invalid. But 1 and 2 are fine. Whereas the question mark says 0 or 1, but no more. So in this case, an empty vector is fine, and a vector with 1 element is fine. But once we go to 2 elements, it's no longer valid. So these are your basic quantifiers. There's 2 more regular expression operators that you can then combine all together. One is cat, which stands for concatenate. So this is just saying, first this thing should be in a sequence and then that thing. This should come before that. So here I'm saying that any sequence which has first a number and then a keyword is valid. an interesting thing to note here is that the syntax says that we need to give each element that we're specifying a name. So here I'm saying the first thing needs to be a number, and I'm going to call that num. I could also have called it quantity or any name that makes sense in my program. And the second thing is a keyword, which I'm calling key. And then if I use this conform function, what I get back is not the original data, but a map using those names. And so Clojure actually has a destructuring feature which works really nicely with those maps. So it makes it easier to process that data later on. The final regular expression operator is the alt, which is the equivalent of the vertical bar, the pipe character in string regular expressions. So this alt basically says it needs to be either this or that. So here I'm saying that something needs to be either a number or a keyword. And so in this case, we don't get a map back when we conform this, but we get a vector back, a tuple of two elements, the first being the name of the thing that matched, and the second being the value, which we then can use for pattern matching. So all of these makes it easier to basically take unstructured data, validate it, but at the same time also turn it into a form that's easier to process later on. So that's those are some of the more interesting ways of constructing specs, some of the more interesting features when it comes to building up these spec objects. Now, what can we actually do with these specs? Because, okay, we already saw we can validate data. That's straightforward. But where it gets really nice is that you can instrument functions. So say our system has a cook function, and it takes a recipe. Then we can use fdef to say that, well, the argument list needs to contain one recipe. And the return value, just making something up here, needs to be a number. Now, when I turn on instrumentation, which is typically something you would do during development, then if I call cook with an invalid recipe, it will straight up blow up and give me that explanation string saying there's something wrong in your recipe. So the great thing about this is that otherwise you might get an error message somewhere down the line, deep down your stack trace, and you don't know where it actually went wrong. And this gets even worse once you're dealing with asynchrony, because this illegal value might have, through an asynchronous CSP channel or what have you, ended up in a completely different stack on a different thread, and now you have no way of tracing back where that faulty value actually came from. So this way, you get sort of early warnings. And they're working to instrument all functions that ship with Clojure. So you're going to get this out of the box with all the Clojure stuff, and also a lot of popular libraries are doing the same. Now that's not all, because what about the macros? So a macro, in a way, is just a function. It's a special kind of function, but to some extent, it's really just a function that takes code as data, takes an abstract syntax tree, and returns some other version of that code as data, and then that gets interpreted as code. So we can instrument these just like other functions, but the nice thing about instrumenting macros is that macro expansion happens at compile time. So remember in the beginning I said that most of the benefits here you're going to get at runtime. You don't really get the compile time checking that statically typed languages get, but by instrumenting macros, you do actually get already at compile time, before any line of code is executed, warnings if you're using macros in illegal ways. So this is nice. The final thing, and I know that this is something that especially gets certain people excited, is that these specs are not only good for validating data, but they can also be used to generate data. And so I think this originally comes from the Haskell community. You can correct me if I'm wrong. The quick check idea, where you're basically saying, here's a certain invariant, a certain property of my function, and now just feed it data, generate random data within certain bounds, and see if this invariant always holds. So here, again, I'm just making up an example. I'm saying that for any recipe, so I'm creating a generator here for recipes, And I'm saying that for any recipe, according to the specification that you can generate, if you pass that recipe to cook, the result should be positive. And now it's just gonna, when I say quick check 100, it's gonna generate 100 random recipes until it finds one that violates this invariant. It not only does that, so I see here it found with fail, found a recipe that caused this to fail, but then it actually backtracks and tries to find a smaller example that still makes it fail. Because when you're dealing with this generated data, you might end up with massive, nested data structures, and then, okay, this might be exposing a bug, but it's very hard to see what's going on. But then because of this reduction, it actually gives you a minimal case that says, okay, well, for this small case already, something's wrong. Either your specification is wrong, or you have a bug in your system. So that's one of the more interesting things about Spec, that it kind of works in both directions. So to recap, clojure.spec gives us a shared vocabulary for talking about these schemas of data. And so across the ecosystem now, we get a way that also programmers can read and see, like, okay, what is the input that this thing expects? We can combine and compose them to build up bigger nested specs. Some of the more interesting features are these key specs for maps and regular expression specs for sequences. We can use them to validate and conform data, and they give us runtime and compile time checks. And finally, they're useful for generative testing. So that's all I have, but I still have a few minutes left, I think, for questions. So thank you very much.
I just wanted to ask, because it seems pretty similar to defining schemas for outsourced data. So is there an idea to use the specs to, for example, cast from JSON files? Because you define that something is a number, and then you can parse the JSON and check if it casts to a number using this spec. It works similar to, for example, schemas in Elixir, or something like that.
Yeah, so I mean, they're basically just functions that you can use however you like, right? So the obvious one is sort of this instrumentation of functions. But yeah, you can totally use this in your web middleware to say, this endpoint expects this kind of data, and then at the same time you also kind of get it back in a nicely parsed format. Or if not, you can send back an error message, an explanatory message to your consuming client. So yeah, I'm sure we're going to see people using it like that.
Is it going to be possible to instrument foreign functions, I mean, from other libraries with specs in your code?
Yes. So instrumentation, so I'm instrumenting here a function in my own namespace, but I could use a fully qualified, including a namespace name of the function there, and that would add that to whatever other namespace, maybe from another library that's coming from. So yes, that's certainly possible.
So I actually have a follow-up question to what was asked over there. Like, is this purely checking, or can you also use this to do some minor type conversion? So to take the JSON example, JSON doesn't have a date format. Could I somehow make this both check that the structure is correct, that the date format is correct, but also get the data back as a date object, or something more close to a date?
Yes. So I kind of had to decided not to go too deep into all the details, but there's something called custom conformers. So you can have specs that don't really check anything, but that transform your data in some ways, and then you can combine those. So we saw the OR, where you say it needs to be this or that. There's also AND, and the interesting thing with AND is that if you use it for conforming, then it passes it through each successive step and conforms it each time. So each next spec gets the conformed output of the previous spec. And then with those conformers, you can basically tag that on at the end, say, okay, if it satisfies all these constraints. For instance, if I recognize it as a potential JSON date, then as a final step, convert it. So yes, that's possible.
Thank you, Arne, for
Thank
your
you very
talk.
much.